All right, so unfortunately, we are not doing the trigonometry unit. You can imagine how sad I am right now. But we are going to push on to the circles chapter. So we're going to push on to chapter 10. And this week we're going to focus on 10.1 and 10.2. So this first video is just going to focus on 10.1. So I will post these notes on Google Classroom for you, and you can fill them in with me as you go. I didn't want to have you writing down a lot of notes in your notebook. And I'll also do a couple practice problems. I would suggest that you pause the video, try them on your own first, and then check your answers with my answers as I go through it. So chapter 10 is all about circles. So a circle is the set of all points in a plane that are a given distance from a given point in that plane. So the given point is the center, and the given distance is the radius. So radius is the distance as well as the segment that joins the center to a point on the circle. Okay, there are what are called concentric circles. So two or more coplanar circles that have the same center are considered concentric. So you'll notice that this smaller circle has the same center as the one surrounding it. Congruent circles are two or more circles with congruent radii. So if the radii are the same length, then the two circles are congruent to each other. Similar to how when you have triangles whose sides are the same length and the angles are the same, then they're congruent to each other. Okay. A point is inside or in the interior of a circle if its distance from the circle is less than the radius. So think about it. In this picture, here's the radius. Okay. Which one of these points is on the interior or the inside of the circle? A is. So A's distance from O is less than the distance of the radius. Okay. A point is on the outside or in the exterior of the circle if its distance from the center is greater than the radius. So here's my radius, but while I'm outside the circle, so C is on the exterior. And a point is on the circle if its distance from the center is equal to the radius. So if I were to draw this line right here, you could see that the distance from O to B is the same length as the radius, so B is on the circle. Okay, so that's the differentiation between in, outside, and on. Here's another review term. So a chord is a segment joining any 2 points on a circle. Think about what's a special type of chord that passes through the center of the circle. The diameter. So we kind of talked about this already when we did inscribed angles, but the textbook is just reviewing it a little bit. So diameter, radius, and then there's your chord. Remember, the end points are on the circle. It doesn't pass through it. Another topic that the textbook is going to review are the formulas for area of a circle and circumference of a circle. So if you haven't forgotten me, you know I say apple pies are 2, or A equals pi r squared for the area of a circle. And then circumference, we've got 2 formulas. It just depends on which one you remember. If you remember my cherry pie is delicious, then it's C equals pi times diameter. Or you could do circumference equals 2 pi r. So I think you all have those pretty ingrained in your memories by now. The distance from the center of a circle to a chord is the measure of the perpendicular segment from the center to the chord. So what does that mean? If I want to know how far a chord is from the center of the circle, the distance that I'm referring to is the distance that is perpendicular to that chord. So that is how we can find the exact difference. So that's going to come into play later when you do some of your homework problems. And if you think about it, if we're involving right angles, we're probably going to involve the Pythagorean theorem. So at the end of 10.1, there are 3 theorems. Now, we're not going to do proofs with these theorems, but we are going to do some algebraic work with them. So the first one is Theorem 74. If the radius is perpendicular to a chord, then it bisects the chord. So what it's basically saying is I have this radius AB. Okay, we have chord DC. And if this radius is perpendicular to that chord, then it should bisect it in half. Now, how can we prove that to be sure? So let's say I draw in these two radii, AD and AC. We know that those two are congruent to each other because of our theorem 19, where all radii are congruent. You can also see that we have this piece right here, AE, and we can use the reflexive property. So you may start to see where I'm going with this for proving that a radius perpendicular to a chord bisects it. So I've got two pieces. I've got these right angles, okay? So if I were to keep going and if I was going to prove this out, you can see that I can show that triangle AED is congruent to triangle AEC, and that would be by HL, right? Hypotenuse leg. If I have a right triangle and the hypotenuse is congruent, so that would be the radii, and they have a congruent leg, so that's the shared piece, then the triangles are congruent. So therefore, DB must be congruent to BC by CPCTC. So that's how you prove Theorem 74. Theorem 75 is the opposite. If you can show that a radius bisects a chord and it not a diameter, we're just talking about chords that are not diameters. So we're saying that those two are congruent. Well, then we can prove that there's an right angle formed in here. So, all right, we could say that EF is congruent to FD. If I draw in my radii like I did in the last example, I know that AD is congruent to AE by theorem 19. And let's say this would be like our given. Okay, so radii are congruent. And then we've got that reflexive property again. I'm not going to write that one out. But you could see, again, we have two congruent triangles. We've got AFE is congruent to triangle AFD. Not by HL this time, but by side, side, side. So we could say that angle AFE is congruent to angle AFD by CPCTC. We could also say that angle AFE and angle AFD are supplementary because they form this straight line. So there's our SA sub. So for those of you who remember way back, if you can show that two angles are congruent and supplementary, then therefore they are right angles. So we can say angle AFE and angle AFD are right angles. And what's the reason why? RAT, R-A-T. So that goes way back. But that's the proof for why when you have two, when a radius bisects a chord, then you know the radius is perpendicular to that chord. Theorem 76, a little more simpler. Basically, if the perpendicular bisector of a chord, it passes through the center. So that also takes us way back to our good old friend PBP, perpendicular bisector. So basically, if we know that DC is a perpendicular bisector of AB, well, then we know by PBP that any point on this perpendicular bisector is going to be equidistant from the two endpoints of the chord. So that must mean that somewhere along here, we're going to say maybe here, I'll call it F, has to be the center of the circle because the radii are going to be equidistant from those two endpoints of the chord. So by PBP, we know that a perpendicular bisector of a chord will always pass through the center of a circle. So that's 10.1.